If we're going to get some number use out of chemistry, then titrations are a pretty good place to look. And a titration in general is just something where you have a species of known concentration and you use it to find the concentration of something else. And this is going to come up with acids and bases. You can do redox titrations, or really you can come up with any titration you want. And the idea is you have some neutralization where you're using a species of known concentration and I'll abbreviate our concentration here, to find the unknown concentration of another species. All right, so that's the basics of it. Qualitatively speaking, we're just talking about adding one thing until the other thing is used up stoichiometrically equal amounts. Only we're keeping track of the exact amount of one thing used, and then we're going to use that to figure out the amount of the other thing. And when we say neutral, a lot of people think of acid and base chemistry, and the truth is acid and base chemistry is a huge place for titrations. So as we look at this real quickly, commonly used for acid-base chemistry, and you can use it for like redox titrations, for oxidation reduction reactions. A real common one would be permanganate and peroxide. The permanganate reacts with the peroxide to decompose into oxygen. This is purple. It goes colorless as the titration happens. So colors are a really good tool in titrations and keeping track of where the end point of the titration is. What we're going to focus on in this video are the acid-base titrations, and we're going to look at titration curves and things like that. So when we look at our acid and our base, and I'm going to try and do some color coding here, blue for base and red for acid, which is a common way that we set that up, and then green for neutral. And I'm just going to uncap these markers and leave them. So the way this works is you can, for this acid-base chemistry, you can use an acid or base, and I'll put in parentheses here, or base, of known concentration to find the unknown concentration and the order reverses on this of a base or acid. All right, if we look real quickly, base, base, acid, acid. So you can use an acid to find out about a base, and you can use a base to find out about an acid. And it's another like half step up in terms of common practice to use an acid or base to find out about a base or acid so that you can find out about an acid. In fact, I'll write that in a minute here. So you can't use an acid to titrate an acid. I'll just put base. All right, so you can't use an acid with an acid, you can't use a base with a base, and if you run into that situation, so you would commonly, you'd use the acid, some known concentration of an acid, and then you'd to find out some base concentration, which you would then use to find the concentration of the other acid, right? And let's just get some things in here. Acid, 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 base, and base, and base. Oop, missed an acid. All right, so as we're looking at this, there's a characteristic graphical representation of titrations, and that's something we really need to spend some time on. And we can look at that surprisingly and get good qualitative information, but we can also get really good quantitative information, and I guess that's the basis for titrations. So we will look there. And let me just... All right, so that's what we're going to be looking at. And typically, and I'm going to draw a couple different pictures here, but the first one, we're going to look at pH, since we're dealing with acids and bases. And I'm going to look at the titration of a strong acid with a strong base, and I'm going to look at the titration of a weak acid and a strong base. So for our title here, I'm just going to say titration of some acid with some strong base. And so what we're doing is we're adding base, and the moles of base are what matter, but that's proportional to the volume that we add. So typically you'll say like volume of base added. And there'd be some concentration and other things. So the two curves that I want to look at here, in fact, we'll look at the first one, and that is just a generic titration curve where you start with some acid that has some pH, and then as you add base to it, that pH starts to go up, and then eventually that pH jumps drastically, and then it kind of starts leveling off again. So that's your typical strong acid with strong base, and I'll try and put that over here, I guess. This purple line is going to be our strong acid with strong base. All right, and again, you start out with a low pH, it jumps up like that. Now, very important note here is that right in the middle is what we call the equivalence point, and that's a vocabulary term we're going to have to come up with. I lost my green marker, so I'm going to have to go with this not green marker. The equivalence point for our strong acid, strong base titration happens at a very specific location. So if you have some strong acid like HCl and some strong base like NaOH, you're going to get NaCl and water. All right, water, for practical purposes, neutral, and NaCl, if you look at the videos about the acid-base nature of salts, sodium is the conjugate of a strong base, it's essentially neutral. Chloride is the conjugate of a strong acid, it's essentially neutral. So this is neutral, and this is neutral. So this point right here ends up neutral, which at 25 degrees Celsius is a pH of 7. Okay, and so this volume right here, I'm just going to label it as VE for our equivalence volume. That is the volume at the equivalence point. All right, so this is a strong acid, strong base titration. Adding base, pH goes up as it becomes less acidic, more basic. And then there's a very quick jump here, and then it tapers off here. And there's specific reasons why those different points on the titration curve exist. And just for reference now, and maybe we'll pick this up in a different video, I want to look at the titration of a weak acid with a strong base. And maybe we can put this in brown here. First of all, if you're starting with the same concentration of a weak acid, the pH is going to be higher. All right. So this brown line here is going to be weak acid with strong base. And so it does not continue up with this exponential curve like that. It actually tapers and then jumps again, and there's a very specific reason for that. And I'm going to try and represent it in some meaningful way here. So it does that, and then it's going to jump up and pretty much follow that. All right, and it's not the prettiest titration curve, but what I'm going to say here is that after our equivalence point, it pretty much follows that same behavior. And we've got some numbers to back that up. What you'll note first is that this equivalence point right here does not match the pH of our other equivalence point. The volume is going to be the same, but the location is a little different. So if I follow this over here, this pH is going to be greater than 7. And there's a specific reason for that. This isn't the straightest line. And our equivalence point value here, assuming we started with the same volume and the same concentration of our weak acid, this number is going to be the same. But we do get that pH greater than 7. So if you look at some titration of a weak acid with a strong base, like HF with NaOH, you might end up then with something like NaF and H2O. And H2O, for practical purposes, is neutral. And NaF, it turns out, is slightly basic. And if you're wondering why, acid-base nature of salts, sodium, essentially from NaOH, the conjugate of a strong base, is neutral. And fluoride is the conjugate of a weak acid, so it's a weak base, all right? So this is a weak base. So when I use up all of my HF and I just have NaF or F minus remaining, we end up at a basic pH. That's why we end up right there. Now, the reason these two curves are the same here, rather important, and we'll have to address that as we look at the individual titration curve videos. But I just want to mention we need some definition of this equivalence point, and then I'm going to highlight what I feel is probably the most important thing to get out of a titration, and then we'll skip to some other videos, all right? So this, we're having a color crisis here. This point right here, or this point right here, these are our equivalence point. Again, for a strong acid and strong base, you end up with a solution that ends up pH neutral, but we're adding the same amount. So the idea for this equivalence point is that the amount of base added, the moles of base added, are equal to the moles of acid you started with, all right? So the moles of base added are going to be equal to the starting moles of acid. All right, because you have used up that acid with your base and you haven't put in any extra base yet. So like the key idea for titrations is that moles equals moles. So I'm going to put that in, and I tell my students, like, I remember one thing from high school chemistry about titrations, and that was me saying to my teacher, like, I have no idea how to do these calculations. What do I do? And he just said, you're overthinking it. Moles are equal to moles. Whatever amount you started with is the amount you added. So moles are going to be equal to moles. All right, that is the basic idea of a titration. So again, equivalence point, moles of base added equal to your starting moles of acid, and we'll work a little bit more with that in the next video.